Thank you. It's my great pleasure to introduce this session on Ngawha. It's a joint presentation between myself and Bignall. I'll do most of the talking. If there are any difficult questions, I'll point at him. What I'm going to do is illustrate for you, to help you with understanding the development philosophy behind Ngawha geothermal field. And I'll illustrate with a little bit of history, but also the philosophy behind the production management. First of all, Ngawha geothermal project is located in the northern part of the North Island of New Zealand, and it's quite a long way from most of the other projects on the top of the volcanic zone. So the operator of the project is Top Energy, and a 10 megawatt plant was installed in 1998 and expanded in 2008 to a 25 megawatt operation. The photo you see at the top there is of the first two units, totaling 10 megawatts. They are ORC, or organic Rankine cycle plants, constructed by Bromley. And this is a project, a geothermal project that was designed at the outset to be managed to avoid all significant surface environmental effects and impacts. That means no adverse effects from the pressure or temperature changes on the hot springs. And that means from the start there was full reinjection of all the fluid produced from 1998, except for a small percentage, about 1% of carbon dioxide gas initially. There was supplementary surface water injected that started in 2008 to sustain the pressure, and this was to replace the mass totally, including to take into account the effect of cooling of the reservoir. And the purpose of this, and it has worked it's been a very successful project, the purpose of this is to maintain the surface thermal features, which are very precious to the community that live in the area. There was no production cooling so far from reinjection returns, and in 2015 we were involved in assisting Top Energy with granting obtaining consent for expanding this operation by another 50 megawatts, and they expect this to be commissioned in around 2019 to 2022. And this is a map illustrating the existing and planned pipeline routes for the production of the geothermal fluids. This is units 1 and 2. The 10 megawatt power plant is located on the western side of the field, and the expansion of 15 megawatts to 2008 is located here. The production wells are located here, and the green line shows the existing pipeline route. The injection wells are located on the eastern side. The planned expansion will include drilling of more wells to the north and some reinjection wells out further to the east. So that's the overall plan for the expansion of the project. The history of exploration and development at Ngawha involved the use of geophysics, of course, and this was the original outline of the extent of the field based on standard DC resistivity measurements. Subsequently, some MT surveys were collected, and the area of the resource was expanded to the north. What was found, of course, which makes the Ngawha field somewhat different from the Taupo volcanic zone field, is that there's very little earthquake activity, very little seismicity, and there's no reported induced seismicity. So it's one of the quietest regions in terms of earthquakes in the whole of New Zealand. And the argument has been made that because this is less active in terms of its current tectonic activity, then tectonic stresses alone are probably not sufficient to maintain the permeability of the host rock. The host rock for this reservoir is illustrated in this slide, which shows you that the production zone is mostly in this grey-wacky basement. So it's a fractured reservoir hosted in a grey-wacky basement with a very competent cap rock over the top. sediment. A little bit more detail in terms of where the wells are and where the geophysics boundary is from the DC resistivity measurements and from the MT resistivity measurements. The important wells to remember for the subsequent slides are the production wells Ngawha 4, located here to the west, and Ngawha 5, which is the hottest well, is not actually connected to the production system at present, and Ngawha 9 is another production well located in the centre, and injection wells are located out on the eastern side. So if you can remember those locations when we move on. The MT data was interpreted in the traditional way to show that there is a conductive clay cap. We know from the geology that this is a sedimentary sequence near the surface, quite low resistivity. And what was difficult about the interpretation of the MT here is that the geology itself has a low resistivity. So it's a conductive clay cap, but it's within a conductive tertiary sediment containing lots of mudstone. So that made it very difficult to define the boundary of the system based on the resistivity alone. There was some indication of doming, of a higher resistivity underneath where the production wells are, but the resistivity didn't give a particularly good indication of the boundary of the system. Having said that, there was a very interesting interpretation made of the gravity survey, and this is a contour map illustrating gravity data, Bouguer anomalies. And the interpretation is that this Bouguer anomaly, which is a gravity low, suggests a possible heat source for the geothermal system. And the heat source from the model that has been constructed from this gravity survey suggests that it might be an intrusive of this sort of dimensions, 5 by 13 kilometers, for the gravity contrast of minus 300 kilograms per cubic meter, and a depth of 3 to 5 kilometers. The argument is that perhaps this is a cooling rhyolitic pluton, quite a large volume. It still has a residual heat of approximately 500 degrees. That has a very high heat content, and the current surface discharge of 17 megawatts of heat loss suggests its age would be comparable to about 40,000 years. And that is in the same sort of time frame as the investigations have suggested some of the geology, the ages of some of the volcanism in this region. So it's not active like the Taupo volcanic zone, but there is some evidence of magnetism, of intrusion in this over this time frame, 40,000 years. If you have any questions about that, you'll have to direct them to Greg, the geologist. Then I'm moving into a little bit of reservoir physics. We're going to hear shortly from John Bignall about the reservoir model, but essentially it's hosted in the Ngawha reservoir, and at this depth range here we have a conductive temperature gradient going up to 300 degrees at the bottom of this permeable reservoir. We have a conductive temperature gradient in the cat rock above. And the conceptual model cross-section that's been constructed from the information from the wells suggests that we have a circulating fluid system with overflow in the north near this well Ngawha 5. I told you that was the hottest temperature, over 240 degrees, rising from depth, and then cooling to the south where we have temperatures about 190 degrees from the southernmost well Ngawha 7. And this again is a conceptual model of the hydrology, showing that where the upflow is occurring in the north, there is some vapor separations and vapor loss from boiling. We have a two-phase and rather gassy zone with quite a high concentration of carbon dioxide, and that's where most of the CO2 comes from. We have this impermeable cap above it, but we have a little bit of leakage up through a few fractures into the near-surface environment. And this shows the resource areas again, a map illustrating the area that has been drilled, so that's the extent of the confirmed resource. The southernmost well, I told you, is cooler, 190 degrees, the northernmost well is hottest, and the expansion area, the production expansion area, of course, for the new wells will be in the northwest part of the drilled part of the resource. Further to the northwest, there is some evidence of some old geothermal activity, some cinders, and some warm springs. And once again, the heat source is postulated to be some kind of cooling intrusion down at maybe 5 kilometers depth. Now, a little bit of information about some of the monitoring that's been going on in the chemistry of this reservoir in the last 15 years. This is a plot of the changes over time, the weight percentage of carbon dioxide in the total discharge from the fluids. You can see there's been a decline over time from about 1.2% originally down to about half of that, 0.6%. And this is explained in terms of the CO2 emissions from the power plant. So they're not, the CO2 is not injected, and so of course that re-injected fluid is lower than CO2, and what we're producing from that in more recent times is a lower CO2 fluid. Again, John will explain this in better detail in the next presentation. This is a plot showing the history of carbon dioxide to hydrogen sulfide over that time frame. And again, you can see a decline from about 110, ratio 110 down to about 70. And the explanation for this is the difference in solubility between carbon dioxide and H2S, and that some more of the H2S is returning into the reservoir with the rejected fluid. And this is a plot showing the changes in geothermometer temperatures. So these are temperatures based on the chemistry of the fluids. We have geothermometry from the sodium-potassium ratio, from the sodium-potassium-calcium ratios, and from chalcedony. All of them have been quite stable. So this is a good indication that we do not yet have any indication of cooling of the reservoir from the injected returns. Reservoir fluid is still being produced at quite high temperatures. And then finally, there are some small trends in the chloride. The total discharge chloride has dropped from around just over 1250 ppm down to just under 1250 ppm. So they're quite minor changes in chloride. And the chloride-boron ratio has increased very slightly. That's also quite a minor change. And then we come into the issues that the consenting process addressed. That the project was to be consented for expansion, 50 megawatts. The operators needed to address these main issues: hot spring interference potential, that is, flow rates, temperatures, and chemistry of these thermal features, which, as you can see, are very popular for bathing. And the subsidence potential and the induced seismicity potential. Well, quite clearly, the induced seismicity was not a major issue because there have been no induced events recorded in the project in the last 15 years. So, although it cannot be dismissed as not never going to happen, its potential is quite low. Subsidence, we addressed that issue, and I'll show you a few slides. But before we go there, I wanted to show you this aerial photo of the thermal features. And there are three main areas: the Tiger Bath area, the Wairiki area, where there's a feature that's been monitored called Universal Spring, and the Gins Bath area, where there's a feature monitored called the Jubilee Spring. And these areas have very different chemistries. I'll explain that in the next slide, which shows a cross-section through those springs going from the highest elevation, the Tiger Bath area, through to the lowest elevation. Three features with different chemistries. This one here has a higher chloride, so it's mostly chloride water that's been pushed up to the surface from the overpressured reservoir fluids. Then that fluid has been mixed with bicarbonate waters, which come from near-surface groundwaters with carbon dioxide dissolved in the groundwater. And then this fluid consists of mostly bicarbonate mixed with acid sulfate fluids. So within a very small distance, just 500 meters, we have three different geothermal fluids in the conceptual model. And the idea was to see if we could look at monitoring of the chemistry and the flow rate and the temperature of those features to see if there's been any change over time. This timeline here goes back to 1945. So there's some chemistry dating right back of these two features. The Jubilee one, as I mentioned, is the highest chloride feature. The universal one is the one that has a higher bicarbonate and a small amount of chloride. And all of these features, the monitoring shows that there's a large scatter, a large variation in chemistry and in flow rate and in temperature, but it's difficult to see any overall trends in time. Production started in 1998, so of course there's good data from 1998 in terms of monitoring. The only trend that you might derive from this data is the universal feature, but as you can see, it started a decline in chloride well before the production started. So there is really no evidence of a significant response of these surface thermal features in terms of their chemistry, or their flow rate, or their temperature in response to production. And that was the most important aspect of the sinking process that we had to address. But of course, one other aspect was the one of subsidence, which is quite a major issue in New Zealand, because several projects have had quite large amounts of subsidence, and I mean 15 metres total subsidence in the Ngawha field, and 3 metres in the Ngawha field. And here the total subsidence that's been recorded is of the order of 5 centimetres, so it's a lot less. It's an order of magnitude lower than the other major projects, but it's still that it's something that's being monitored and something that is being modelled. This was the historical data. The next plot shows the historical match, which is the model to the historical data in terms of trends. That's a reasonable match. It's a model that Bignall put together using the top 2 reservoir model and then calculating from the pressure and temperature changes in each plot of the model, what the effect would be at the surface of each of these locations, and these are the well sites. And there's a reasonable fit, and then this data was then projected forward to see by 2050 how much additional subsidence there would be. And you can see it reaches a total of about 0.05 metres, or just 5 centimetres, just that much. So this is actually a very minor effect, and should have no real influence on the infrastructure, the housing, the pipelines, etc. at the surface. So that was an important conclusion from our modelling. This shows a contour map of the simulated subsidence out to 2050, and you can see the maximum is quite low, 0.05 metres, and that covers a large area within the centre of the field. These are the well sites, the production well sites, and the reinjection well sites, and it's dominated by a cooling effect, fluid going from the injection wells towards the production wells. There will be a cooling contraction effect, which is the dominant influence on this substance. So that is my summary of the science that was put into the expansion proposal for this Ngawha geothermal project. And so I thank you for your attention. I'll pass it forward.